Okay, so for part 1 of 4-2 notes here, we'll pick up, hopefully get about halfway through maybe, or close to halfway through at least. But anyway, so we're going to talk more about restoring forces, Hooke's law. Once again, there's not a whole lot of new material here. There is a little bit of calculus though, so please do pay attention once we get to that part. But hopefully a lot of this is just recap for you guys as we work through this section. But anyway, restoring force is any force that restores an object to equilibrium. So the common situation that we hopefully all kind of realize is a spring system, right? If I compress a spring this way, then the restoring force is pushing it back towards its equilibrium position, which would be somewhere maybe over here, right? So if I've compressed it with an applied force, we know the spring force would be pushing back opposite that direction. The other example though would be something like a pendulum, right? If I take a pendulum and I pull it from its original position down here, then its restoring force is going to be the force that's pulling it back towards equilibrium. So it's going to be that component of gravity that's pulling it back towards that equilibrium position. So you should be familiar with that term of a restoring force and kind of what its attempt to do is. Elastic systems, any of those that exhibit a restoring force, so springs, rubber bands, and so on. So technically you could make an argument that a pendulum does have some type of elastic nature to it. However, we'll see that more with simple harmonic motion later on, so we won't worry about that as much right now. But anyway, let's enter into this. So how do we find the force exerted by a spring, right? This is perhaps the most forgotten equation we see in Physics 1, right? How do I find the force exerted by a spring? And the answer is not 1/2 kx squared, right? The spring force, the elastic force of a spring is negative kx, right? Or just kx. Now the negative implies, once again, that the direction is opposite of the direction that the applied force is. But once again, truly the equation is just negative kx. So there's my force for a spring, and then what are some of the key graphical features? Well, if I'm talking about an ideal spring is one in which the spring constant is a constant. And so if I look at the graph for an ideal spring, well, where should it start? If I don't compress it at all, so if this is a force versus a displacement graph, if the displacement is 0, shouldn't the force then be 0 as well? So that tells me that the ideal spring, it should start at 0, 0. And then from there, it should just be a linear equation, right? It should be a straight line that goes off from that. The steepness of the line, what would that tell us? Well, if I think about it, right, the first questions I want you to always think of when you look at a graph, what does the slope mean in this case? And what does the area mean in this case, right? Those are the first two questions I always want you to think about when you see a new graph. Well, the slope would be my change in force, my force over my displacement. Well, if I solve this equation for k, I'd get k equals force over displacement. So the slope is my spring constant, right? That's what the slope represents on a force versus displacement graph. What about the area underneath the curve? Well, what does force times distance represent? Well, force times distance is the work done, right? Which we'll look at a little bit more here later in this chapter. But anyway, those are the first two questions I do want you to be thinking about. Right? So the slope is the spring constant, the area is the work done by the spring, or the energy stored in the spring. Right? So those are things to make sure you're pretty comfortable with. Because of that, right, what's the relationship then between force? So if I give you force as a function of displacement, and I ask you to find out something about the work or the energy done, how do I do it? Well, it would be the integral of the force function, right? If I know force as a function of displacement, then if I integrate that, I'm finding the area underneath the curve. So the integral would represent the energy or the work, which is a good thing to make sure you're thinking about. Once again, I'm probably getting a little ahead of myself, but it is a good thing to be comfortable with. Right? Anyway, the other way that you could find this, so is, again, the work is the area underneath the curve. Well, isn't that the area of a triangle for this spring? So it'd be 1/2 my force times my delta x, but the force for a spring is just k times x. So if I substitute that in, I get 1/2 k times x times another x, or better yet, 1/2 kx squared, and hopefully that equation looks familiar, right? That is the work or the potential energy stored in a spring. Right, so anyway, these are all represented by a graph. You should be pretty comfortable interpreting graphs for all of that information moving forward. So once again, some noteworthy observations here. Right? The spring force is defined as negative k delta x. Again, the negative implying it's the opposite direction of the applied force. delta x being how far it's stretched from equilibrium. So keep in mind, this is not the total length of the spring, right? It's not the total length, it's just how far it's been stretched or compressed, right? So it's the amount that it's been stretched or compressed. So make sure you are always very careful with that. And then the spring force is directly proportional to the displacement. That makes sense, right? The displacement goes up, then you would expect the force to go up as well. This can only be used for an ideal massless spring, right? We will see some springs where they are not ideal or they are not massless. Now, for most of those springs, what they'll do is, like I mentioned on the last page, they'll give you a function. So they may say that f of x equals some function. Maybe instead of negative kx, it's negative kx squared plus 2x plus 5. Right? So they'll give us some function, and then you have to be able to use this function and use some calculus to find the information we want. So that is something to keep in mind as well. Right? So it's not always just k times x, but most of the time it will be. So let's look at an easier example here. Right? So the figure shows a spring attached to a 2 kilogram block, the other end pulled by a motorized toy train that moves forward at 5 centimeters per second. 5 centimeters per second, I am going to go ahead and convert that to meters per second. Right? So 5 centimeters per second would be 0.05 meters per second. So for what it's worth, I converted that. The spring constant is 50 newton meters, or newtons per meter, and the coefficient of static friction between the block and the surface is 0.60. The spring is at equilibrium length originally, so it's not originally stretched or compressed. When the train begins to move, when does the block begin to slip? And this one we're simplifying a little bit because we are actually going to assume that it's maintaining a constant speed of 5 centimeters per second. In actuality, the reason that doesn't really make sense is if the train was going forward this fast, but then as the spring stretches, wouldn't it be pulling back harder and harder? Right? So we wouldn't necessarily expect that to be a constant velocity. But we will go ahead and keep it simple and assume that it is maintaining a constant 5 centimeters per second. Right, so when is the train going to begin to move? Well, what has to happen in terms of static friction? Well, for this block over here to move, we know that right now it's at rest. As the train stretches, there's going to be a spring force pulling both this way, right, and then back on the train. But as the train stretches, so we've got a spring force pulling this way, and we'll have static friction that begins to oppose the spring force, right? So when is the train going to move? When is the block going to move? Well, the block is going to move once the static friction is less than, right, the spring force applied, right? So the maximum static friction would have to be less than the spring force applied. Well, the maximum static friction is my coefficient times my normal force. The spring force is just going to be k times x, right? K times the displacement. So if I look at this here, they give me the coefficient. It is on a horizontal surface, so it's the full 2 kilograms times 9.8. It's the full force of gravity for the normal force. And then the spring constant they give me of 50 newtons. So the only variable I have right there is delta x. So then I can solve for delta x, and then once I do that, since I know it's moving at a constant velocity, I can find out when, I can find out how long it's going to take to slip. Right? So in solving for delta x, what this tells me is delta x has to be greater than 0.235 meters. Right? So once it's greater than 0.235 meters, that's when it's going to slip. Again, I'm assuming that it's traveling at a constant velocity, and because of that, I can use velocity equals delta x over t. So I know the velocity is 0.05 meters per second. I know that it needs to go 0.235 meters. So I just need to figure out how long that's going to take, because they asked me when, right? Not how far, but when does that start to slip. So then solving for t, it tells me it's going to be about 4.7 seconds. So really, after 4.7 seconds, anytime greater than 4.7 seconds is when it's going to slip. But anyway, hopefully nothing too tricky with this example. Again, just getting comfortable with kind of my spring force, which I know we sometimes forget that equation. But anyway, let's look at a quick concept question, and hopefully a pretty easy one here, but it is a very important one too. So the graph shows the force versus displacement, right? So it shows the force versus displacement. Sometimes they do use delta S instead of delta X, but they're really the same thing. Rank in order from largest to smallest the spring constant. Well, again, just like I mentioned previously, right? On a graph like this, you need to realize that the slope represents the spring constant. So the one with the largest spring constant is going to be the one with the largest slope. So the constant of A is going to be greater than the constant for B, which is going to be greater than the constant for C. Right, so hopefully that one's pretty easy to work through. Nothing too tricky, just looking at which one has the steepest slope. So then probably the last part I'll get to here in this first part of the video, and it goes back to kind of like what we saw in the first section where we had to do some calculus. So let's look at Hooke's law, which is the spring force, right? It's the equation for a restoring force. Let's look at that in terms of calculus and integration. So again, very similar to what we just did on the last example page. So again, Hooke's law, the spring force says force equals negative kx. Well, force is really the net force then if this is the only force acting. So my spring force would be equal to my net force. So really what I'm doing here is I'm extending that to say then that mass times acceleration equals negative k times x. Well, once again, the key to these type of integrations is if I realize that the acceleration is really just the change in velocity with respect to time, then I know that this is really just mass times dv over dt. I do know that looks like a d theta, it should be dt, equals negative kx. So once again, just like we saw for our conservation of energy in the previous part, the trick is I'm not going to just use dv and dt. I'm actually going to break dv over dt into dv over dx times dx over dt, and once again I'm going to realize that this portion of it, this part right here, just represents the velocity. Alright, so that part right there just represents the velocity. But anyway, so then I have mass times dv over dx times dx over dt equals negative kx. And here it does get pretty interesting, right? I hope obviously you guys are starting to get more comfortable with this, but it should be pretty cool when we actually do the integration for this. So again, this whole thing right here is just the velocity. So I've got mass times velocity times dv over dx equals negative kx. Now the difference this time, when I multiply both sides by dx, right, I am isolating my variables and I do have an x on that side of the equation. So whereas in the previous one, on the previous example page, when we didn't have an x on the right hand side, we actually do have an x over there now. So I have mv dv equals negative kx dx. So once again, the dv, the dx, that's telling me I need to integrate both sides with respect to either v or with respect to x. Right? So on the left hand side I integrate with respect to v. Once again I increase the power by 1 and then divide by that new power. So I get 1/2 mv squared plus some constant. On the right hand side I get negative, again I'm integrating with respect to x, so very, very similar, right? 1/2 kx squared, and hopefully that looks right, like it's ringing some bells. And then over here I have a second constant. So then when I solve this out, I'm going to go ahead and move this to the left hand side, so I'm going to add that over. And then I'm just going to subtract the c1 over to get some new third constant, right? So I end up with 1/2 mv squared plus 1/2 k times delta x squared equals some new constant, right? So again, what this is showing me using Hooke's law, and Hooke's law again applies if there are no outside forces acting, right? So this applies if the only force acting is the spring force. But by using Hooke's law, I can show once again the conservation of energy is upheld, right? My velocity, my kinetic energy, plus my spring potential is always going to be equal to some constant value. So my initial and my final measurements are always going to be equal to some constant value. It's a very, very important conclusion. It's a very, very powerful statement that allows us to use some integration, some calculus to relate it to energies. So again, kind of the key concept that comes from all of this. One, I do want you guys to be comfortable with these, right? So you very well may see on a test or a quiz where they ask you to do this for either the spring force or for the net force, and I do expect you to be comfortable with that. The other conclusion I want you to be comfortable with, though, is if I give you the force as a function of x, again, if you do the integral of that, you're finding a function that represents either the energy or the work done in terms of x as well, right? So it is very important that we kind of take a side note and realize that that's also a relationship. You'll see several graphs or several equations in your homeworks that take advantage of this relationship here. But anyway, I'll go ahead and stop the first part of the video here since it's a pretty good breaking point. Again, if you do have any questions over this type of stuff, guys, don't hesitate to come find me and let me know.